So, just to review what these terms are, this is your flux. This is your macroscopic cross-section. Or scatter. And this is cumulative. So just like in the problem we had where we had 2 fuels and 1 moderator, when you go to evaluate this, you're going to have to find capital sigma S for all the materials you have in your reactor. And this again says that you're looking at the partial of the flux with respect to the axis that you're trying to define neutron current density in. We didn't really get to this the other day, and I'm not sure where you stand in your calculus, but I'd like to go through that very quickly. So, if I gave you the equation...
Professor?
Yes?
We can't see the board because the camera is focused on the book.
Okay, sorry about that.
Thank you.
Okay, could you follow over here, or do I need to go over that again?
Maybe just the last part.
Okay. If you do that triple integration, we're going to come up with the neutron current density from anywhere in the plus Z side of the whiteboard. So this is the XY plane. This is the plus Z side, which is out in the room when I've turned this sideways 90 degrees. So my little window is right here, but it shows up as a slit when I turn it. This is my little window, if you're out here in the plus Z direction. When I turned it 90 degrees, XY plane plus Z side minus Z side. And again, all we're looking for is the neutrons that are going through this little window. So going from the plus Z side to the minus Z side. So we would show this like this. This would be in the minus Z direction, the neutron current density. It is a vector. And again, I encourage you to put the little 0, because the little 0, which you see here, here, and here, your book did not put it here. The little 0 denotes the location of where you have your window. Because remember, I could put my window right here. I could put my window over here. You're going to get different values. Then, going back to this is your flux. This is the macroscopic cross-section for scattering. And remember, it's equal to the number density times the microscopic cross-section for scattering. So when you have multiple fuels, multiple moderators, like in the example we did earlier, plus the one quiz you did, this is going to be a composite value for 3 things: 2 fuels and 1 moderator. This is the partial of the flux with respect to the axis that you're looking to find the neutron current density. So, since I'm not sure where you are in your calculus, I was next going to go through that. So if we have an equation, y is equal to (3x squared plus 2x plus 1). If I take the partial of this with respect to x, I expect everybody could do that. So that's going to be 6x plus 2. I can also put this as this way, where this is a regular d, because we know y is strictly a function of x only. Okay. Whenever you see a sort of script, then you know that there is more than one variable that impacts the other one. So in this case, we have, for my original equation, we have two variables, y and x. In this particular case, x is the independent variable, y is the dependent variable. And I'm sure you're familiar with that. You could plot x and y, all that kind of good thing. Now, let's say we're looking at a different type of equation. Let's say that w is a function of x, y, and z. And in particular, the equation is 6x cubed e to the minus 4x cosine of 6x excuse me, gotta change that, y and z. So w is a function of x, y, and z. X, y, and z are the independent variables. W is the resulting dependent variable. So if I go to look how w varies with any one of these variables, I can look at how it varies with respect to anything. And let's say I do it with respect to x. So this sort of script D alerts you to the fact that w varies by more than one variable, but we're just looking at what happens with x. When you do that, you treat everything that is not this variable as a constant. So all of this stays exactly the same. So we can put that up front. Then we're going to differentiate.
Does that say -4/2?
Excuse me?
What does that say on top of the e? E to the negative what?
4y.
Okay, thank you.
Okay. Times the cosine of 6z. So since this does not have an x in it, it stays the same. And then you only differentiate what's inside here, which would be 18x squared. So if I put things back in its original order, this is going to be 18x squared e to the minus 4y cosine of 6z. Okay? There might be some reason where you need to take a differential of this again with x. If you do, that would show up this way. So you do this same thing again over here. This now becomes d2 of w, and then dx2, because you've done it twice. Again, you do the same thing. You keep everything that doesn't have that the same. Then we differentiate just what's in here, which would be 36x. So this now becomes 36x e to the minus 4y cosine of 6z. Let's say you need to take this, and then you need to, for some reason, differentiate it by y. Okay? So now we're going to take this, differentiate it by y. So this now becomes d3w dx2 dy. And you sort of read the order that you've done the differentiation, going from left to right in the denominator. This time we keep everything that's not y constant. So this is 36x cosine of 6z Now we differentiate that, and if you remember how you do that, that's going to be the same thing, e to the minus 4y. And then you differentiate just what's in the top, which would be minus 4. So this then becomes minus 144 x e to the minus 4y cosine of 6z. And you could keep on going as long as you wanted to. If you needed to do another one that was a function of z, then this would be d4w dx2 dy dz. Again, we keep everything that's not z the same, so this would be minus 144 x e to the minus 4y. And then we differentiate that, which is minus the sine of 6x times what's inside, which is 6. So this whole thing becomes, I'll just write it up here, minus 144 and 6 is going to be minus 4, 2 up to there, 6, 2 up to there is 8. I did that right off the top of my head. 846 x e to the minus 4y times the sine of 6x, but that minus comes up to here to make that a plus. So this is okay. Have you gotten that far in your calculus yet? Or maybe had it before in some other aspect? Everybody following me with this, hopefully. Any questions on that? Okay. So, now I'm going to erase this. Okay, so in this particular case, when we found out what the neutron current density was going through our little window in the minus z direction, we got this. You would need to know what your flux was in this particular instance. You'd also need to know what materials you had so you could calculate the macroscopic cross-section for scatter. Okay. So in this particular case, what you would have determined is what is the leakage of neutrons in the form of a flux through my little window going in the minus z direction. As it turns out, you could have done this. Go back and look at my same little window. Okay. But this time, look at all the fuel and moderator mixtures in my fist that are behind the blackboard. And I'm looking at any of those that are going to be generated out of my hand, three-dimensional, heading like a flashlight cone towards this little window, and then actually the ones that are scattered en route. You're going to end up solving a same type of equation. And when you do that triple integration, what you're going to find out is, if this is my little window, what is going in the plus direction, wherever my little window is. If you do that, again, it's a vector. Again, it'll have units like in flux. And when you solve that, that is equal to so my neutron current density going through the little window in that direction, because this is the plus z side, so that's why that's z plus, is the flux at my little window divided by 4 and then minus 1/6 macroscopic cross-section for scattering, again with the partial evaluated at my little window. One way that I like to remember these things is, if this is a minus, this is a plus. If this is a plus, this is a minus. That's a simple way to do it, okay? Now, we have said we've got a neutron current density going in that direction. We've got a neutron current density going in that direction. So if we combine the two, if we say if we look at what's going in the plus z direction through my little window, and we look at what's going in the negative z direction through my little window, that will be the total neutron current density going through my little window in the plus z direction. So if we did this, and let's say this direction was 4 times 10 to the 10th neutrons per square centimeter per second. This guy, when you did all the math, turned out to be 6 times 10 to the 10th neutrons per square centimeter per second. When you looked at this difference is 6 minus 4, or 2 times 10 to the 10th neutrons per square centimeter per second. So that would mean your total leakage in the z direction going through this little window is plus 2 times 10 to the 10th going in that direction. If you have a 3-dimensional reactor, which is what we're going to be working with, instead of putting our little window like this, so it's going through in that direction, we could turn our little 1 centimeter this way. And then we could look at everything above this axis. So we're looking at everything on the plus y side. So if we look at that, everything up here on the plus y side going through the little window in this direction would be y minus. Again, my little window is oriented here, so everything down here, down to infinity, going through in this direction, it's going to be plus. If we compare this number to that number, we find out what the total leakage is in the y direction. Likewise, we could orient our little window in this manner. Everything that's on this side would go through in that direction. That would be jx minus. Everything on this side going through the little window would be jx plus. And again, if we look at the difference between these two, we would find the total difference going in the x direction, and it's referenced as a neutron current density with the units of neutrons per square centimeter per second. We're talking a little bit of math, but a lot of concept right now. Are you hopefully, between the book and myself, following what we're doing so far? Okay. If I go back, and I look at the z, we know that total neutron density in the z direction is equal to again, looking at our little window. When you take this expression, and if you remember the other expression was when we take these two and we add them vectorially because they're vectors, you come up with minus 1/3 macroscopic cross-section this is the total neutron current density going through my little window. If you did that in each direction, so that you had an X and a Y, this is going to be the total value Instead of thinking of this as a little 1 centimeter by 1 centimeter area that my neutrons are going through, when I look at each of the directions, X and Y and Z, my little 1 centimeter by 1 centimeter window actually becomes, if I can draw this correctly, a little 1 centimeter by 1 centimeter by 1 centimeter cube. And if this is where my window is for 0, what I'm basically going to have out of this, and I'm just going to invent a direction, I'm going to have a neutron current density perhaps going in this direction. I might have a neutron current density going in this direction. And let's say the final one is coming out of the board. So my total neutron current density is the sum of these three vectors, three-dimensional. So it's this guy plus this guy plus this guy. So the total neutron current density from my point is from the origin here to the end of J sub Z. But I can find out what that is. If we combine all of those together, your book then defines this term as D. So D is equal to 1/3 macroscopic cross-section for scattering. And they call this the diffusion constant. And this is going to be a physical property of your system. It's all going to depend on the materials you have and their scattering values. So you can write it like this, or your book also shows you a different way you could have written this. So this could also be minus D times all of this, or it could also be minus D times the gradient of the flux. And the gradient of flux is exactly what that is. This is a shorthand for this terminology. When they do that to come up with an exact value, this D is equal to 1/3 sigma S, but they also modify this to allow for forward scattering in your material. This is typically going to be very close to this, and this is called sigma transport.
Does that say 1 minus cosine
Yes,
-4?
psi minus psi, which is the angle of
Oh,
scattering
okay.
in the electric system. And there should be a little line over there for the average value. And if you remember that, We said that that average value is 2/3a, back in the last chapter. Okay. We now have enough basic information to try to develop the diffusion equation. So what we've done thus far is we have introduced the concept of neutron current density. We've shown how you can calculate a value going through a little window in any direction that you want. This is the basic equation for looking at one direction. We can come up with the net going through the window by looking at what's going in one direction versus what's going exactly opposite to come up with a total leakage or total neutron current density in that direction. We know that in real life this is going to be a three-dimensional reactor, so we have to look at leakage three-dimensional. So we have to add each contribution together. It's a vector quantity three-dimensionally, so we're adding those vectors to come up with the total leakage. Now we're going to develop the diffusion equation, and I'm going to do that, and then we're going to take a little break, and then I'm going to come back and we're going to rework the problem in your textbook for the earlier materials we had with carbon and uranium-235, look at how that would be influenced in our case. That's all I'm going to cover today, but then you're going to have the take-home quiz that I inadvertently sent you on Wednesday, or maybe Friday, I guess it was. It'll be due on Wednesday. Okay. And if you want to follow along in the textbook, this is going to be from page 257 through 259. Your book establishes the little cube. It looks at what's going in each direction. So if I turn this a little bit, this is the x direction. We might have a neutron current density going in the plus direction. We might have one going in the minus direction, depending upon what we have for fuel and moderator on this side compared to fuel and moderator on that side. So we could come up with a total neutron current density, which is a function of leakage in just the x direction. Just to give you an idea on this, let's say we have a fuel and moderator mixture. Let's say in the y direction, that this fuel and moderator mixture goes to infinity. Let's say in the z direction, in the minus z direction, the fuel and moderator mixture goes to infinity. Okay. This is not going to happen in the real life, but it's a way you can understand things and then go to apply it to three-dimensional models. Okay. When we do this, there's going to be no neutron current density going in the y direction because we have equal fuel and moderator mixture in each direction. Same thing for z. But let's say in this that this is uniform. This is plus x, and this is minus x. Let's say, and this is the center line. Let's say we pick a point right here, and we established a little window in the x direction. So this is our window. The little window really looks like this, 1 centimeter by 1 centimeter, but I've turned it sideways because we're interested in what's going for the neutron current density. So when we look at this, anything that's going through in this direction is going to be Jx plus, because it's going in that direction, it's perpendicular, and we could find out that value by going back to that original equation that we had. If I extend this line to infinity for both y and z, anything that's fuel and moderator mixture on this side of the window can generate neutrons to go through that little window to be in the Jx plus. Conversely, I still have my little window, but now I'm looking at all the fuel and moderator that is on this side of this line that can now generate neutrons to go in the form of neutron current density back that direction. So that direction is going to be Jx minus. And wherever my little window is going to define the point of interest or the point of measurement. So if I look at the total neutron current density at my window is Jx plus greater than Jx minus. Are they exactly the same? Or is Jx minus greater than Jx plus? Which one of those is true and why? You have a 1 in 3 choice, or chance, should I say. Anybody? Everybody totally lost?
Wouldn't Jx minus be greater than Jx plus because you are on the positive side of the origin, which means you're going to have more negative than positive? But you're going to infinity, so.
Well, no. Any other guesses and why? When you look at all the fuel and moderator mixture that is on this side of the window, there's a lot more fuel and moderator mixture here, because you have this plus to infinity, plus to infinity. So you have a lot more fuel and moderator mixture to generate neutrons to go through the little window. Whereas on this side, you have much less material for fuel and moderator, and again to infinity, to go that direction. So Jx minus, in other words, what's going in this direction is going to be less because more of it is going in that direction. So what's going through the little window in that direction, because we have a lot more fuel and moderator, is plus. What's going from this side is generated by that amount is that. And Jx plus would only exactly equal Jx minus exactly at the center line. When you have an equal amount of fuel and moderator mixture on one side compared to the fuel and moderator mixture on the other side. And again, in order to evaluate that, you'd have to know exactly what the flux was at the point of interest. If we took this all the way to the boundary, let's do it on this side. If I put our little window right there, right at the physical boundary of all our fuel and moderator mixture, we could still determine what do we have for neutron current density going through the window in the plus x direction. We could also determine what's going through the window in the negative direction. In this particular case, you have all the fuel and moderator mixture here to go in that direction. On this side, you don't have anything to generate neutrons to go back in this direction. So this is much, much greater than, excuse me here. This value is very large. Excuse me, this value is very small because there's nothing here to go back this direction. All of this can go back in this direction. So wherever you put the window, you can look at the total fuel and moderator to get a feeling for what's going in each direction. For 3 dimensions, you're going to look at each of the 3 directions to see how that flux is impacting the neutron current density, is impacting the number of neutrons that go through that little window. This is actually called an infinite slab. And this is what I'm going to be working a problem on Wednesday of this week. Okay, to go back to the diffusion equation again. So we now have developed, when we looked at our little 3-dimensional 1 centimeter by 1 centimeter by 1 centimeter cube, we've developed a term for total neutron current density. This is related to leakage. They showed you how to develop a leakage expression. And again, this is following on that foot pass. And this is equal to minus D del 2 flux. And I'll go through. Del is an operator, and it depends on what system you might be looking at.
Marker. Should have no markers in my room.
Make sure they work before you go. Because they dry out.
Yes, they do. Sorry to interrupt.
This blue one will work, sort of.
Got a red one here that works.
Okay, you bet. And this del operator will relate back to geometries. So for example, if you look at, if it's 3-dimensional rectangular, this would end up being so if this was acting on a rectangular coordinate, you'd be applying this del operator on this, so it end up looking this. So this is what you have, this is what you have, this is the shorthand as to how you denote it. So this is the term for leakage. If we go back and look at the rate of change of neutrons in my reactor, we know we can always state the rate of change of neutrons for anything with respect to time is production minus loss. And where does our production come from? Our production comes from thermal neutrons created from thermal fissions. That's our only production. What do we have for loss? We have two. We have leakage, and we've just determined leakage, and then we also have absorption. We have expressions for this, we have expressions for this. We've just developed an expression for leakage. So if we combine them together, if we look at the production, and again, you might want to follow this on page 258. So this is production. And then we're going to have a loss, which is leakage, and leakage is minus d del 2 flux. And then if we look at absorption, again, that's a loss, so that's going to be minus macroscopic cross-section for square absorption times the flux. In this production, this assumes all neutrons are instantaneously reduced to thermal energy. Production, loss due to leakage, loss due to absorption. If we then go back, since this is steady state, we know that's exactly equal to 0. So we could then write this your book then says, okay, let's divide everything by sigma A. Cancel, cancel. 0 divided by anything is still 0. So now we have 0 is equal to K infinity flux plus, and now they relate another term, which is so this becomes, if you're following along here, L squared if I sort of reorient this, if I then look at my flux as a common term, this part could become so I'm taking the flux out of this, so this is now this. If I then divide everything by L squared, what I end up with then is 0 is equal to, cancel, cancel. This is the diffusion equation. So it tells you what is happening to your neutron population in your reactor. You typically see this rewritten, though, by putting the 0 on the other side. So you have del 2 flux plus K infinity minus 1 over L squared flux is equal to 0. As it turns out, this is defined as B squared, where B is buckling. So when you do that, this finally reduces to this is the general diffusion equation. B is buckling, and the reason it got that term is this equation is like buckling for a column in civil engineering. Civil engineering was around a lot longer than nuclear engineering was. So when the original engineers saw that type of equation, they adopted the term buckling, and it's stuck ever since. So today we've identified what leakage is. We've developed neutron current density to help define leakage. Once we've defined leakage, we put it in an equation for steady state reactor, looking at the one production source, the two losses, to come up with our general diffusion equation. So this is good for any fuels, moderators, mixture. It is also good for any shape. So this is where I want to stop momentarily. Why don't we take about a 8-minute break? We'll come back, let's say a 10-minute break then. We'll come back about 8 minutes of 2. And then I'm going to take this and we're going to determine buckling for the problem that was worked earlier in the textbook. Okay. When we start to work these problems, hopefully you'll get a little bit better warm and fuzzy feeling as to how we use these, how they've been developed, and how we're going to apply them. So later today after the break, we're going to determine buckling for our U-235 and carbon that we had earlier. We're going to review that a little bit, and then I'm going to give you a take-home quiz, which you already have, to develop buckling for beryllium and uranium-233. When we come back on Wednesday, I'm going to take this and we're going to work the one in the book for the carbon and the U-235, and we're going to show how you would do that, how you would put that into a shape that is an infinite reactor. Then the next thing we would do after that is take that same material and put it in a shape for a cube, three-dimensional solid. And then, depending on time, we may look at other rectangular solids, a sphere, a cylinder. Everything, though, will go back to using this original equation, where you can use variations of the solution to this equation with boundary and initial conditions to solve any combination of fuel moderator mixtures in any shape we might have. Okay, I've taken another couple of minutes, so we're going to now come back at 5 of. Any quick questions? Okay. When we come back at 5 of, I'd like you to bring your textbook. I'd like you to have it open to page 260. And notice I've also paperclipped that, because as we go forward, when you're doing different fuel moderated mixtures, different shapes, in addition to the other one that you have penciled that you're going to go back and you can always calculate K infinity, this is the page you can always go back and calculate buckling. But I want to go through this solution with you, and then we'll go over the quiz assignment I gave you. I'll see you at 5 of.